Let's talk about visual relocalization. Firstly, create a map from a set of post-RGB images. Secondly, given a new query image, estimate the camera's position and orientation. For this task, learning-based relocalizers exhibit exemplary accuracy. They treat the mapping images as training set and encode the map into a network. Let's train the state-of-the-art relocalizer DSAC star and watch how it learns the map. Now, we wait. In fact, we have to wait for a long time. DSAC star needs 15 hours to map a single scene. This is where ACE comes into play, accelerated coordinate encoding. Let me show you what ACE can do after 10 seconds of training. The query input here is a video, but we only use single RGB frames for our pose estimates. There is no tracking. We need 5 minutes mapping time to achieve state-of-the-art accuracy. That is a 200 times speed up compared to DSAC star, or a 300 times speed up on a consumer-grade GPU. ACE is the first learning-based relocalizer with high accuracy and practical mapping times. To understand how it works, let's take a look at DSAC star and at the reason it is so slow. DSAC star follows the framework of scene coordinate regression proposed at CVPR 10 years ago. Let's consider this place again. Each point has a unique 3D coordinate in the reference coordinate frame of the map. These are called scene coordinates, and we can visualize them by mapping the XYZ coordinate of each point to the RGB cube. Given a query image that we want to relocalize, we utilize a neural network that we trained to predict the scene coordinate of each pixel in the image. The network's prediction induces a dense 2D-3D correspondence field from image to scene. We can use RANSAC and PNP to infer the query pose from those correspondences. How do we train the network without ground truth scene coordinate labels that would require depth or a 3D scene model? DSAC star trains in 2 phases that both take roughly 7 to 8 hours on modern hardware. In the first stage, DSAC star minimizes a pixel-wise reprojection error. In the second stage, DSAC star minimizes an image-wise pose loss using differentiable RANSAC. The second stage is a refinement that ACE will not need. Let's focus on the first stage. This is the reprojection loss we optimize. In each training iteration, we take one mapping image and let the network predict scene coordinates. Using the ground truth pose of the mapping image, we project the scene coordinate into the image. And we measure the residual error with respect to the position of the pixel the scene coordinate was predicted for. This loss uses only single view constraints. Hence, the depth of scene coordinates is ill-defined. But throughout training, the network sees many different mapping images. It converges to a scene representation that is consistent across views, with scene coordinates having their correct depth. Now, why is this taking so long? DSAC star optimizes the network one mapping image at a time. The prediction is dense, the loss is pixel-wise, and each mapping image has a lot of pixels. But the prediction for neighboring pixels are very similar, so are their losses. A single mapping image offers only limited training signal and a coarse gradient, paid for with a lot of redundant compute. We need small learning rates to slowly converge to the optimum solution. What we want is stable gradients with high learning rates to converge fast. ACE revolves around the idea of optimizing over all mapping images in each single training iteration. We cannot simply increase the batch size to multiple thousand images unless we want to buy our 5 minutes training time by using a GPU cluster. Let's take a look at the DSAC star network and see what we can do. We have a fairly standard CNN. A few convolutional layers with redos, a few downsampling steps in the beginning, the occasional skip connection. The network is fully convolutional with a limited receptive field. That is, it takes an image patch and maps it to a single scene coordinate. The network slides over the input image, reusing computations from neighboring pixels to produce a dense output. So, the network is convolutional, but not all convolutions are created equal. Here we have 3x3 convolutions and 1x1 convolutions. In fact, after some point, we only have 1x1 convolutions in the network. Let's split the network at that point, which gives us a CNN feature backbone and the regression head. The regression head is a MLP, since it consists only of 1x1 convolutions. This distinction is crucial for the training speed of ACE. The feature backbone needs spatial context for its predictions. It needs access to neighboring pixels to map the input image patch to a high-dimensional feature. The regression head does not need spatial context. It merely maps the high-dimensional feature to a scene coordinate. For ACE mapping, we use a pre-trained scene-agnostic feature backbone. It processes the mapping sequence and predicts high-dimensional features for each image patch to fill a training buffer. This is a data preparation step that takes up the first minute of our 5-minute training regime. After the data preparation step, we start the actual mapping process. First, we shuffle the buffer. The only thing that is actually trained for a given map is the regression head. We pass it a batch of buffer features. It predicts scene coordinates, and we calculate the reprojection loss. Repeat. Note how each training batch contains features of random mapping images. We optimize over hundreds or thousands of images at once, which makes optimization extremely stable, and we can use very high learning rates. For relocalization, nothing has changed. We combine the trained regression head with the pre-trained feature backbone. Given a query image, we predict scene coordinates and use RANSAC and PNP to estimate the pose. There is a lot more to explain. How we pre-train the feature backbone, how that feature backbone compares to superpoint, disk, and the like. How we mimic DSAC star's end-to-end training with a curriculum over the reprojection loss. Why we predict homogeneous scene coordinates. You find this information in the paper. Our maps are privacy preserving and only 4 MB large. Despite those tiny maps, ACE can represent large areas well, as we see here. For top performance on larger areas, we can utilize an ACE ensemble. We cluster the mapping poses and train one model per cluster. Given a query image, we run it through all the models and take the estimate with the highest inlier count. We also contribute a new dataset for outdoor relocalization, consisting of 10 scenes. Mapping poses come from real-time visual odometry on the phone. No depth nor a 3D scene model is given. Mapping has to start from post RGB images only. How fast is your method?